Nice to be back here. So just briefly again, we are both working on virtualization related stuff with Sergej. I'm now maintainer of the Zen Hypervisor that you might have heard of, also a library called libvmi and the drug-proof malware analysis system. I'm also, with Sergej, are part of this non-profit organization called the HoneyNet Project. And through that, we have participated in this summer's Google Summer of Code. So a lot of the things that we're going to be talking about today is related to that. So just briefly, what we will do today, I will give a little bit of motivation of why you even want to do malware analysis through the hypervisor, but then we will actually go and do a deep dive into behind the scenes for both drug-proof and Zen and see what's coming up next. So stealth, why would you want to do stealthy analysis of software, right? Well, if you first want to do analysis of any kind of software, what you normally do is you use a debugger, right? That's what most hardware actually has built-in support for. That's what you do. You use whatever debugger you want. The problem with that is that it has a built-in assumption that the software that you are trying to debug or monitor doesn't care that it's being debugged. There is actually an observer effect that the software that you're monitoring can actually detect that it's being monitored, and then it actually can change its behavior. And that's, of course, a problem if you're doing malware analysis because you won't actually observe the desired effects that the malware actually do, so you won't be able to detect that, what is that malware is actually doing. So briefly, let's look at, random stuff you can find in malware. Just by looking at this random stuff, that you can find through running strings on a binary, you can pretty much immediately tell without even reverse engineering what that malware is trying to do here. Pretty much fingerprinting its environment, looking for whatever process is running on that system that would signal to it that, hey, this is a debugging environment. There are some other stuff running on that system that you would not normally see on a production machine, right? You would not see WinDebug or OldDebug running on a production system. Of course, there is a bunch of other things that malware can look for in its environment when you are trying to analyze it to bypass you. There is even a Yara signature that you can use to find malware that is trying to detect a debugger in its own environment. So you can actually play that detection against the malware itself to detect malware that is actually trying to evade detection. But it's a cat and mouse game, especially if you're running in the same context as the malware is. So you need to do something better because architecturally, if you are running in the same context, you have no, and you can't be sure that what you're actually observing is real, especially at runtime. So what you can do as a first step to improve stealth from an architectural perspective is to move a monitoring component into the kernel. Create a kernel driver and monitor the execution of a process from the kernel. Architecturally, you are in a more privileged level there. And you can do that, but Windows doesn't actually like it if you just randomly hook stuff within Windows itself, which is a problem because what if you want to monitor rootkits, which are, of course, kernel level malware? You have the same problem there, right? So let's just briefly look at the rootkit problem. This is a random graph from a McAfee report that shows increasing number of rootkits present in the wild. But if you actually compare the numbers, this is still only less than 1% of all malware McAfee reported in 2015. So what that means is that, well, rootkits are not that big of a problem. Or are we just really bad at detecting them, right? Our tools are not really designed to be able to deal with even process-level malware that is trying to evade. How are we dealing with rootkits that are trying to evade? So these numbers are, can you trust them? Well, how can you be sure if you are not doing this type of detection and analysis from a architecturally sound perspective? So that's where we get to hypervisor stuff, right? So let's move everything even below a layer, move it to the hypervisor so that it's even harder to detect what's happening. You have even greater visibility because you can actually have access to all the virtualized hardware, but it's of course a lot easier said than done. Once you move everything out to the hypervisor, it gets very tricky. So that's where we begin. So 2 years ago here at Hacktivity, I released this tool called the drug-proof. It's a malware analysis system based on Zen. If you haven't seen the talk, please go ahead and check it out. You will get some more high-level details about it. In the 2 years since it's been released, the system has been radically reworked. 2 years ago, what I released was academic prototype. There has been over 208 pull requests now merged. It's been totally cleaned up. Parts of it been reworked in C++. So if you actually want to start working with it today, you have a lot more pleasant time than you had 2 years ago. So it's been improved quite a lot. In the 2 years also, the Zen site has been totally reworked. So these are all the patches that I got merged into Zen in the last 2 years that actually have included a ton of bug fixes, and actually the entire interface that is giving you access to this type of monitoring has been totally reworked. So Zen is actually a lot more stable since I started this work. So all right, so that's where we are. We have this system up and running and it's stable, but are we done? Of course, that's where we actually begin this talk, really. Because hypervisors were not really designed to be stealthy either. Just the same way as debuggers were not designed to be stealthy, hypervisors are not stealthy either. So let's take a look and see what we can do about that. So this is a tool called the Paranoid Fish, which is an open source tool that implements a bunch of standard malware techniques that are trying to fingerprint its environment. It's up on GitHub, you can grab it. So if you run it in a VM running on Druckproof, you see a bunch of red things, which are the bad, right? It's like, it's traced, it's detected, something is happening. And that's of course not something you would want to have when you have a stealthy malware analysis system. So let's see what we have here. There is timing-based analysis is happening, CPU ID-based fingerprinting, and also checking for things that are just you won't see in production environments, but are more standard for a sandbox where you have less than 60 gigabytes of disk space or only one processor, things like that. So let's go through this list and see what we can do about it to try to hide that we are actually doing malware analysis through the hypervisor. So the CPID hypervisor guest status is actually a bit in the ECX register that if you execute the CPU ID, the hypervisor can advertise its presence. It's just a bit that it's flipped, and that's what the Paranoid Fish is just checking for. It just checks that bit if it's set. Of course, this is something the hypervisor can pretty easily overwrite, so if you just add this line to your Zen domain configuration, all of a sudden you just fix one of those detection problems. That was pretty easy. The other things that Paranoid Fish checks for is vendor IDs. So the CPU ID actually can include signatures for various hypervisors. So instead of just getting nothing, you actually get, like for Zen, you get this signature called Zen VMM, which is still a static signature that it's baked into Zen, but what you would have to do normally is you would have to recompile Zen and just patch it out so that it's not actually returned, which is kind of a pain. So for Zen 4.8, which is going to be released this December, I introduced this new feature where you can actually subscribe to CPU ID events being executed in a guest, and then you can filter on the fly depending on various things, what is actually being returned for signatures, if anything at all. So I have a little demo for this here. Let's see if we can actually get it working. So this is Zen 4.8, and we have Druckproof running now, monitoring CPU ID stuff, and then I execute the Paranoid Fish, and you see a bunch of CPU ID events popping up right away. Not all CPU ID events are actually being executed by this process. CPU ID is getting executed by other stuff as well, but you will see that Pawfish is there. And then we see that the 0x4 million being checked, and it's reported as trace, right? So this is the default behavior of Zen. It just returns the CPU ID signature, and then it's detected. So now if I add another flag to filter with the -s, what we can do is just re-execute the Paranoid Fish and see what's happening. It's running all the same CPU ID checks. And then all of those checks are now gone. So this is just illustrating the effect of being able to do on-the-fly filtering of CPU ID. All right. So next thing, 60 gigabyte of free disk space is pretty arbitrary. You know, malware can check for any type, any size. But disk is pretty free too, so you could just, you know, pop a couple terabytes of disks into your host and then give as much free space as you want. Or you can even do better. The LVM disk abstraction library actually has this feature for copy on write disk, so you can actually give as much free disk space as you want to your sandbox, and it will only allocate as much new space as it actually writes to. So you can actually, you don't actually need terabytes of disk space. You can pretty easily get over this limit because most malware will not dump terabytes of stuff to your disk. So this is pretty easily worked around with LVM. Other things, uptime check, right? How long has this machine been running? A lot of sandboxes you see actually start a full operating system from scratch. So you would see, you know, the system is running for only a minute before the malware started executing. So here, this is just, you know, random, you know, hard-coded signature for 12 minutes. You could really just create a snapshot for your VM after running it overnight or for a week or whatever. And then restore your sandbox from a snapshot, and then, you know, this check would go away. Or also we could just hook the function that is used for the timing and just return a fake value to it. So this is all pretty simple stuff. We can get around these nice and easy. But this is where things get a little bit more interesting. So memory size check. So disk is cheap and memory is getting cheap as well, but you still have a limit on how much memory you can pop into commodity servers. So, you know, who's using less than 1 gigabyte of RAM, but, you know, maybe malware is going to check who's using less than 8 gigabyte of RAM today. And if you keep adding 8 gigabytes of RAM to your sandboxes, that kind of limits on how many sandboxes you can run simultaneously because you will run out of RAM. But what's nice is that Zen actually has this feature called memory sharing, which is part of some other hypervisors as well. But with Zen, it's actually quite nice because you can go down really deep and do nifty stuff about it. So this is a graph from a paper I wrote where I ran high interaction honeypots with memory sharing enabled. And the blue stuff, or the black stuff there that you see is really how much memory you can save by deploying memory sharing across honeypots. So these were honeypots that were available on the internet, on an academic network that had a bunch of vulnerable services, and I actually saw, you know, bots and whatever breaking into these honeypots, and then I checked how much memory remained shared after a minute or two of malware activity on the honeypot. And if I had, let's say, you know, 12 gigs of RAM, normally I would be able to run maybe 10, 12 honeypots at the same time, but with memory sharing, I could run up to like 37 on the same machine. So this is quite nice. You can really maximize the number of sandboxes or honeypots you're running on a system. So this is really great. Of course, there is a downside to memory sharing is that it degrades over time. So the longer you're running systems that begin with, you know, almost fully memory shared, over time it actually degrades. So you need to be aware of that. Fun fact about this, that I actually tested this honeypot system first live here in Hacktivity, here in this room. And I was really looking forward to people actually trying to break into the honeypot because, you know, it's a hacker conference. Maybe someone is doing something nifty on the network, but actually got nothing. The network here is actually probably the most secure environment you will find anywhere. So didn't really get anything interesting, but anyway. The status of this system right now is that it's pretty experimental. With Zen 4.8, there has been more fixes that I introduced. And also keep in mind that if you're doing memory sharing on virtual machines, you are opening the door for cross-VM rowhammer attacks. There's a paper about that if you're interested, but really, it depends on how long you're running your sandboxes. So if you're running sandboxes for a couple of hours, you might actually see some malware trying to do rowhammer, and then with memory sharing, there is a risk of spilling over, which you normally don't want to. All right, so now we get to this point here, which is number of processors. And this is where things got really complicated simply because of how external monitoring through the hypervisor is implemented. There is a race condition if you are not careful, which you want to avoid. And to understand really the nature of why that is, I'm just going to explain real briefly on how the actual monitoring was implemented in the first release of Drugproof. So it was using the breakpoint instruction 0xcc that was injected into target code locations that I was interested in getting notified when it's being executed in the kernel. And then those pages where these breakpoints were injected were marked execute only in the EPT, which is the hypervisor managed page table for the virtual machine, so that if anything tries to scan the code like the patch guard or Windows, I could actually remove the breakpoint, single step the virtual machine, and then place it back, so the patch guard would not actually be able to see there is anything there, because when it actually fetches the memory, it will fetch the original contents. And then the same thing happens when the actual breakpoint itself is executed. I would remove the breakpoint, single step, and then place it back. And this worked quite well. Again, this is where the EPT is. So you see that it's actually managing the guest physical to machine physical address, and it lives in the hypervisor, so it's stealthy by definition. The problem is that all vCPUs by default on all hypervisors share a single EPT. So even if you have multiple vCPUs, they will share this structure. So when you actually have to relax the permissions on this structure and you have other vCPUs still active, you have a race condition between clearing the EPT and then adding it back. In that time frame, another vCPU that is running could fetch that memory location and you would not be able to detect it. So that's a problem. And it applies to the breakpoint itself as well. If you remove the breakpoint from memory, some other vCPU could be fetching that instruction at the same time and you would miss something. So when you're trying to do malware analysis, it's not nice to have an architecturally weak way of actually logging, because that's, of course, what malware would eventually look for and exploit to stay hidden. So there are some ways that we can deal with this. For example, while we have either the EPT trap or the breakpoint executing, we could pause all other vCPUs at the same time, but that would add pretty heavy overhead to your system. Or there is this other system in Zen that actually has a full-blown x86 emulator within the hypervisor, and there are security vendors building on top of this emulator to do security monitoring, but I'm not a big fan of emulation. It's been probably the biggest weakness in hypervisors, and if we can avoid using that, that's the best. So there's this alternative system that I'm going to let Sergej introduce, because he has been spending quite some time now working with this.
Thank you very much, Tamás. So, as you already suggested, the alternative would be to use the Zen's alternate P2M, or simply short alt P2M subsystem. So what is the cool thing about Zen alt P2M is that it simply extends this original idea of using only one EPT, which is this physical to machine translation or management for the guest virtual machines, and instead it simply uses or provides multiple EPTs per guest virtual machines. So this allows us to provide in the individual EPTs different mappings and also different memory permissions for the guest virtual machine's memory view. This means you can simply say that the Zen alt P2M allows to define, or rather control, the individual memory views of the guests. And what is also cool about it, it allows to dynamically switch between the different views at runtime. So a little bit of background to the Zen alt P2M. This subsystem was originally introduced by Intel exclusively for Intel CPUs. So this subsystem is based upon the P2M subsystem, which is responsible on Zen for the management of guest physical to machine physical translation. And by the way, this is where the P2M comes from, so physical to machine. The original idea of Zen alt P2M was to make use of this interesting function called vmfunc. And this function is insofar special as it provides the ability to dynamically switch between predefined memory views, that is, well, EPTs on x86 at runtime. And this can be even done without switching to the to the hypervisor. This means this original overhead, which we had before of trapping into the hypervisor, is thus eliminated. So in combination with another feature, which is called virtualization exceptions, then altp2m even allows to handle EPT violations inside of the guest, which is pretty cool too. So as you can see, this subsystem, the Zen altp2m subsystem, allows or is quite a neat feature for in-guest monitoring tools, which can make use of it. But also it can be used of by entirely external applications. This means a hypervisor can make use of altp2m to actually manage, or better say, control the guest's physical memory view. So another quite exotic feature of Zen altp2m is called GFN remapping. So as the name already suggests, this feature allows to remap certain guest physical addresses in a way so that they, well, essentially point to a, well, entirely different machine physical address. And this is actually better illustrated on the next slide. So here we have our initial virtual machine monitor or hypervisor and virtual machine guest set up as before. Since the hypervisor uses Zen altp2m at this point, we provide multiple mappings for same guest physical addresses. And this is illustrated here through the different or multiple errors going out from the guest physical address. So now by using this GFN remapping feature, we allow a certain, or for example, one specific view, this is the EPT, to remap this specific guest physical address to point to an entirely different address, which is here illustrated as the shadow copy. So it is not pointing to the original machine physical address anymore. At this point, I would like to provide or hand back the pulse to Tamás, as he can explain how this feature can be used within the context of DrugWolf.
All right, so again, normal mapping with an EPT looks pretty straightforward. It's one-to-one mapping from guest physical to machine physical. There are the permissions, read, write, execute in EPT, and that's how you see it being used by normal hypervisors. Now with DrugWolf and altp2m, what we do is we have this altp2m view 0, where we have, let's say, the target page where we want to inject breakpoints. And what we do is we create a shadow copy of it right next to it, and then we also add just an empty page. And this is actually the view that is used by DrugWolf during execution. So this is the default view, which is another EPT called view 1, where you can actually see the different permissions and the remapping actually in effect. What happens is that the target page is actually now being pointed to the shadow copy, and only the shadow copy has the breakpoints in it. Furthermore, the permissions here are set to execute only, so if code is executing in that guest, it can fetch the code and it will fetch the breakpoints as well. And then if anything tries to read from that page, we can just switch that one vCPU back to view 0, single step, and then go back to this view. Nice thing about that is that this is all vCPU independent. You can switch these pointers with having multiple vCPUs at the same time. Of course, since we added that extra page at the end of the guest physical memory that is used for the shadow copy, we don't want to have malware just be able to scan the physical memory of the virtual machine and see that, oh, at the end of this memory space, I have this duplicate kernel code or whatever code that should not be there. What is that doing there? So what we have is that the actual shadow copy with its own GFN is not accessible at all. So if anything is actually trying to read from the shadow copy, not using the remapped GFN, it actually is going to create a violation. And then we have a second view where the shadow copy itself is remapped to an empty page. So if anything is trying to read the shadow copy, it will see nothing. It will just see empty space. So that the shadow copy is really only accessible when it's being executed. And then we can just nicely switch around these pointers, and the guest VM is none the wiser. And this works really great. And it's very fast because all you really do is you switch a pointer, and that's very fast. You set up these tables at the beginning, and after that, the performance overhead is marginal. As Sergej said, this was originally, auth-P3M was originally designed by Intel to be executed from within the guest using VM func so that they can actually swap around these pointers from within the guest, which is not required for drug-proof, and it's actually a vulnerability if you are using it for malware analysis from only on an external perspective, because you don't want malware to be able to issue a hypercall and then, itself swap around these tables. But we can work around that with the Zen security modules, where you can actually prohibit the guest itself being able to execute this type of hypercall. But setting up XSM is a bit of a pain, so a lot of the bug requests or bug issues I have right now is just people trying to actually follow the instruction on setting up XSM. With Zen 4.8, it's actually been reworked quite heavily, so it's going to be a lot easier going forward with Zen 4.8 to actually use XSM. And that's really was just all to get over this one point here, to be able to run multiple vCPUs in the guest without having a race condition and being able to monitor everything. So that's pretty great, but there's still a couple things left to do here. We still have the traced stuff. One of it is I/O. Looking for mouse activity or keyboard activity and things like that. So since most of those hardware are actually emulated by the hypervisor, we can always just provide fake input, and has been largely been done by other sandboxes as well. It's simply a to-do item. Also, timing analysis. Now, RDTSC is usually the one it's an instruction that reads a timestamp counter, and that's the highest resolution time source you have in a virtual machine, so it's usually used for timing analysis. We can actually trap that into the hypervisor and then provide a fake time to that guest, and there has been work on Zen to do that, but messing with the time source of an operating system is a big can of worms, so this has been pushed to the back of the queue. If someone wants to work on that, that's great. I keep it on the to-do list for now. And it comes to the point where we really need to ask, do we really need to hide the presence of virtualization from the guest itself? Today, virtualization is pretty much used everywhere, so you can make an argument that it's not necessarily required to hide the presence that there is a hypervisor. It might simply be enough to hide the presence of the external monitor. You would not want to have some difference when you have the monitor versus when you don't, which is important. Some new stuff that's also coming up in Dragproof is debug events. So in a couple of years there has been a lot of news about malware employing self-debugging techniques so that you can't attach another debugger to it or can monitor its execution. So for Zen 4.8, I introduced this new feature where you can actually trap debug events, hardware debug events into the hypervisor and just monitor that as well. So if malware is trying to do any type of self-debugging, you would actually be able to monitor that to the hypervisor. So here I just have Visual Studio standard debugger running, some dummy application with a breakpoint attached, and you see it's just, whenever I click on continue, there is a breakpoint being hit, and then the program is just looping. Once I actually execute Dragproof, it's now trapped through the hypervisor, so you actually get access to the hardware debug events through the hypervisor. So if malware is trying to use any type of stealth technique here, you would actually be able to monitor that through Dragproof. So that's pretty nice. This is going to be released with Zen 4.8. That's again coming up in December. While doing this breakpoint with this debug delivery stuff, there has been actually some interesting things that I discovered regarding breakpoints, which is again the 0xCC instruction, and that's these are the ones that debuggers use, and this is the one that Dragproof uses to do monitoring, which means that if anything in that guest uses the software breakpoint, we would have to re-inject it to the guest, which is not that big of a deal. There is a function for Zen that allows you to inject an arbitrary trap to to the VM, including software debug exceptions using this function. But it has an interesting vector here, which is the instruction length. So, the question is, what is the actual length of the breakpoint instruction? And the obvious answer to that would be 1, and that's what we have been using, right? It's a 1-byte instruction. And this has been working fine. There's been no issues with it, except if you actually read what the Intel Software Developer Manual says about int3, that's the 0xCC instruction, what happens when it's actually trapped to the hypervisor is that there is the VM exit instruction length field reported when it's trapped, which should be 1, right? The instruction is 1 byte. But what's interesting is down here in the bottom. It says that in the above cases, this field receives the length in bytes 1 to 15 of the instruction, including any instruction prefixes. How can, an int3 instruction be 15 bytes? That's weird. And the important thing is really what's here in the parentheses, the instruction prefixes. So if you don't know anything about x86 instruction prefixes, they really have absolutely no effect on the breakpoint instruction. So no sane debugger ever adds any. But if you actually add prefixes to it, the CPU will be happy to execute it, and it actually changes nothing about the behavior of that instruction. The CPU actually just skips over the prefixes, except if it's trapped to the hypervisor, it changes the length of the instruction. The weird stuff is that you can actually add the same prefix multiple times to the breakpoint, and that's how you can actually get the breakpoint instruction to be 15 bytes length. And of course, if you are re-injecting that to the guest with the wrong length, you will keep hitting the same breakpoint over and over, which malware could potentially use to detect the external monitor. So this was fixed, but yeah, this was weird. Like, who would have thought that the Intel CPU's pipeline is behaving this way? So, keeping attention to all the footnotes and parentheses in the Intel Software Developer Manual is actually quite important, as it turns out. There is a really nice blog article, if you are interested on how many x86 instructions are there. And the answer to that is actually not quite simple. Depends on how you define an instruction. All right. So that's where we are with x86, but there has been work on actually getting this system to monitor Linux systems, and not just on x86, but also on ARM CPUs. And the interesting thing about ARM is that it now has very similar virtualization extensions since the Cortex-A15. Some things are the same, some things are a little different, but the core concepts are very similar, but devil is in the detail. What I have here is a little demo on actually monitoring a Linux guest on ARM. It's a 32-bit ARM system. It's still using the 4.7 Zen. And we can actually run system call trapping through the hypervisor so that we can actually monitor the execution of that virtual machine. So again, what I do there, I just listed the processes running in that ARM guest, and now I'm gonna start up the monitoring and add the traps to all the system calls. So now if I hit enter and just do stuff, I see all the system calls being executed in Linux on ARM, and it's being trapped to the hypervisor, and then from there to effectively drugproof. Of course, this is still a work in progress, so right now, while this works, this is still not stealthy, so there's still a lot left to do, and that's where Sergej has been actually quite involved, so he's going to continue with what's left to do with ARM.
Thanks again. So, yeah, when it comes to the ARM architecture, we have a handful of issues which simply complicate the process of stealthy guest monitoring. So the first thing is that at this point in time, we simply don't have alt P2M support for the ARM architecture in the mainline Zen kernel. So the next point is that the ARM second-level address translation mechanism doesn't have a concept of executable memory, and this complicates things. This means, if we look at the x86 architecture, as before Tamás already explained, we can simply inject certain software breakpoints into the code and hide it by simply remapping the page to be execute only. This means every read or write access will be tracked by the hypervisor or even by the guest, depends on the architecture extensions, and can be changed in a way so that they will be satisfied without actually revealing the monitor, right? So on ARM you can't do it this way, and because of this you will need to come up with more sophisticated solutions as simply remapping the memory, because every time you map the code into the memory it needs to be, and it is hardware defined, it needs to be readable and executable. So the last point, or the last issue when it comes to stealthy monitoring concerns the single stepping. So there is also no stealthy single stepping mechanism on the ARM architecture as opposed to the monitor trap flag on Intel CPUs. Well, as part of this year's Google Summer of Code, we have tackled this first problem, namely, or concerning the missing alt P2M support for the ARM architecture. Google Summer of Code is a cool event for students which would like to participate in open source projects. So Google invites students and supports them to do that. And this is exactly what I did. So as part of this year's GSOC, thanks to Tamás, thanks to the HoneyNet project, I have implemented the Zen alt P2M subsystem for the ARM architecture. The current, or our current extension to the Zen hypervisor comprises about 38 patches and is available on GitHub. So please go ahead, check it out, and tell us what you think about it. Although you can, as you can expect, that, well, a large patch series like this is or can be rather demanding to be actually merged into an open source project like it is the case with Zen, we still expect Zen alt P2M for ARM to land in Zen version 4.9. We have implemented the entire functionality which has been already present on x86, or more precisely on Intel CPUs, and extended it in a way that you can now say that our implementational concepts are rather hardware independent. Of course, assuming the hardware supports virtualization extensions, but you can take it and more or less port it to other architectures as well. On the other hand, of course, we have also extended the implementation in a way so that it better fits the ARM architecture, and these differences become visible, especially when it comes to TLB handling. So that's that. What's next? What are our next goals? So we tackled the next problem, namely the stealthy single stepping on ARM as well. And therefore, we did the following. This is actually our most recent work. So we used the Zen alt P2M subsystem and extended it in a way so that we were able, or we actually managed to use Zen and Zen alt P2M to desynchronize the split TLB organization on the ARM architecture. To be more precise, we were able to do it on ARMv7 and ARMv8 architectures as well. So while this approach works, well, surprisingly well and actually also stable, it has its limitations, of course, and we believe that a knowledgeable attacker will at some point be able to resynchronize the TLBs again, and hence, eventually find our monitoring application. So because of this, we extended the approach, and instead of desynchronizing the split TLB architecture, we partitioned the entries in the TLBs so that the individual partitions can be now associated with the individual memory views which are provided by Zen alt P2M. So, and this architecture, this final architecture allows finally to also stealthy single step applications on the ARM architecture. Unfortunately, I can't go into much more details at this point as we are still during the publication phase, but please stay tuned and look forward to our next talk. At this point, I would like to conclude. That was it from our part. Thanks for coming. Thank you for your time. Thank you for your attention. If you should have questions, I'm not sure, do we have time for answering questions right now? Otherwise, we will be heading downstairs and waiting for you. Thank you very much.